Hello there and welcome back. So with the theory on EXTI, NVIC and interrupt out of the way, this is time for us to get started writing some code. So we're going to continue from where we left off in the previous video where we learned how to de-initialize GPIO pins. I'm just going to modify this code so that this time around when we press the button, it's going to toggle the LED. So what that means is that if the LED is already on, pressing the button will turn it off. And if it's off, pressing the button is going to turn it on. But instead of doing it in the loop here where we'll do HAL GPIO read pin, it's called polling, right? So you are basically using the processor's time to check whether the pin has been pressed or not. Instead, this time around, we are going to use interrupt so we don't have to manually check. Okay, so let's get started. So we know from previous videos that our LED is connected on pin 9 of port E, and that is why on line 6 here we enable clock access to GPIO port E, and this one is enabling clock access to GPIO port A because that is where the button is connected. Okay, so this right here sets GPIO pin 9 on port E as an output pin. So I'm going to move the HAL GPIO init call right under it so that we've grouped it nicely, and I'm going to get rid of this. Then we will reuse the same GPIO init type def instance, which is CFG here, to configure the button. But this time around, we are going to configure it to raise interrupt when it is pressed. Okay, so I'm going to say CFG.pin, and we know that the button is connected on GPIO pin 0. So this is where you also want to visit your reference manual to see which pin connects to what. And then here, this is where you want to pay attention. So I'll say the mode is equal to GPIO mode, IT rising. So look at it. These are all the interrupt types that I mentioned in the previous video. That it could be an interrupt detection on the falling edge. So falling edge detection basically means that the pin is high and it is transitioning to low. A rising edge detection means the pin is normally low, and when it's rising to high, this is where we want to detect or we want to signal an interrupt. Here is GPIO mode interrupt rising and falling. So what this means is that whether it is falling or rising, we will still raise an interrupt. In this particular case, because we know from the previous video that the button on my particular board is connected as a pull down, what it means is that normally it is reading low, and when you press, it reads high. So what it means is we are interested in raising an interrupt on the rising edge. Okay, and all that we now have to do is to call HAL GPIO and init. So then we have to pass GPIO A, and then we pass a pointer or a reference, depending on which language you're coming from, to our configuration init type def data type. So here I can put a line here so that you have that visual context to help you understand things properly. So here I'm just initializing the whole HAL SDK. I'm enabling clock access to the different GPIO ports that we use, one for the LED, which is port E, and one for the button, which is port A. And then I create a value of type GPIO init type def, which helps us to configure the GPIO pins in the very specific modes that we want. So between line 11 to 14, what's happening is I'm just setting GPIO pin 9 as output push-pull mode. It's not pulled high nor low, and then I initialize that. And then on line 17 all the way to 19, what I'm doing is I'm configuring pin 9 to raise an interrupt when there is a rising edge detection. So when you press it and it's rising, this is where we want the interrupt to be raised. And then you call GPIO in it also so that it is configured that way. Now, one very important thing that we want to do is we have to enable interrupt detection on that particular line. And to do this, we have to tell the NVIC. Remember the theory from the previous episode. So we say HAL NVIC, and there are a lot of functions that helps you to do things with the NVIC. Some has to do with even setting priorities of your interrupt. So I didn't mention this in the previous video. Let me take a brief moment to mention it, that interrupts also do have priorities. And what it means is that a higher priority interrupt can interrupt a lower priority interrupt whilst it is executing its ISR. An ISR here is an interrupt service routine. And it is done so because obviously certain actions are more important than others, right? For example, this is a very hypothetical example. Let's say you are building a firmware for a lift, right, or an elevator, for example. If there are buttons in the elevator for emergency situations, you expect that these buttons will have higher priorities in terms of interrupt, right? Because yes, even though the elevator is busy taking a human being to another level in a building, if that human being has an emergency and presses the button, you expect that the processor will give priority to that emergency over everything else. So even though we won't do it in this video, in subsequent ones I'll show you how to play with the priority settings of your interrupt service routines. But for now, we are just going to enable an interrupt. So you call the function HAL NVIC enable IRQ. IRQ stands for interrupts request. Okay, and see what I'm going to pass here. I'm going to pass EXTI 0, and this is one of the things I don't like about this ID, is about their IntelliSense. Is an ugly one, but that's what we have to work with. So you remember from the previous video how I explained that the EXTI is a peripheral that helps the microcontroller unit to sense external interrupt. There are some interrupts that are internal to the processor, for example, or exceptions that are internal. So for example, if you access an array index that is out of bounds, or you try to access a memory that is not within your power to do so, or you try to divide by 0, you know, all of these are happening internally. And then there are external interrupts like what we detect from GPIO pins. Okay, there are other sources of interrupt, like I mentioned. It could be that you've set up a timer, and by the way, we talk about timers. You've set up a timer to notify you when a particular number of milliseconds elapse. All of these things are happening based on interrupt. Now, because GPIO interrupts are external, it has to go through the EXTI interrupt peripheral. And like I mentioned to you, hopefully I still have the image here. Yeah. So our button is on PA0. So that code we've written right here, this code, is basically telling the NVIC that it should be checking the EXTI for an interrupt that could come on EXTI 0. So what that basically means is that any of these pins here could raise that interrupt, and it will be sent to the NVIC on EXTI 0, because remember, this is a multiplexer and it is taking input from every pin 0 on all the various ports, right? So you need to enable it so that NVIC knows which of the registers it has to check to see whether an interrupt has happened or not, so that it can tell the processor to go in there and execute the interrupt service routine. So that brings us to the next question. Okay, we have set up an interrupt here that some interrupt could be happening on EXTI 0, and the reason I chose 0, remember, is because the button is connected to pin 0 on port A. Okay, and port A, pin 0, so pin 0 port A is connected to the EXTI peripheral through EXTI 0. Be careful not to type 10 when you mean 0. It is EXTI and then 0. So if you want EXTI 10, it has to be EXTI and then 10. It's a very common mistake, so you want to check it if your button happens to be on EXTI 10. Okay, back to the question I asked. Now we have notified, sort of alerted NVIC that it should be checking for the possibilities of interrupt happening on EXTI 0. But the question is, okay, so if this interrupt happens, what should the processor do? Remember, we said the processor executes interrupt service routines, or ISR, in response to interrupt that occurs. So this ISR is nothing but a function name, and it is a special function name because it has a special region in memory where the processor expects it to be, so that the moment NVIC tells the processor that, hey, there is an interrupt on EXTI 0, the processor knows, okay, let me pack up the status of the program I am running, the stack frame, the variables, the register content, the program pointers and all that, store them somewhere, and that is called the context switching. And then I have to go to whatever is the interrupt service routine for this particular interrupt kind that has happened. And after I am done executing, I will come back to continue my program. So one key thing is, how do you find the names of these interrupt service routines? That is going to be the topic of the next episode, because I will dive deeper into this section here, the startup code, and I will show you some things in this assembly line here, assembly code here. But basically, there is a standard, there is a format to how you get to know what is the name of the interrupt service routine. For EXTI 0, you want to write a function. So the signature is void and then EXTI 0, and then you bring IRQ handler like this. It takes no argument and it returns nothing. Okay, so how did I know? If I copy this function name and I come to the starter file here, this file is written in assembly, but if I search for EXTI 0 IRQ handler, I can see it here. I don't want to go too deep into the startup for now because I'll have a dedicated episode to it, but the take home I want you to have is that the names of these interrupt service routines have already been defined in the startup file, and it is in a section called the vector table. We talk about that in a separate episode. And the reason I said it's a special function, it's only special as far as the name that has been used in this vector table is concerned. If I change the name here to something else, I just have to make sure that I am defining the same function name here, and it's going to work. All right, and it doesn't even have to be in the main file. I can actually put it somewhere. Like, actually, the way the STM Cube set up the project, it actually expects that interrupt handlers will be in this file .it.c. So the it here is for interrupt, but I don't want us to do anything with any of the code that was generated for us, and we will talk about this file when we are talking about the vector table. So for now, let's close it, and I will put it in main.c. It doesn't matter where you put it because all of these C files will be compiled together into the same binary. Okay, now before we start writing the code for what should happen when the interrupt service routine is running, keep in mind, this is very important, that you don't want to do long lasting things in interrupt service routines. Remember, it's an interruption, and something is saying, hey processor, I need your attention now. The processor doesn't have to go in there and spend forever there. So how we usually use interrupt service routines is to toggle some flags, right? So you can have a global variable that is a flag, and then when the interrupt happens, you change the state of that flag so that based on the state in your normal loop, you can take an action based on that. But in this particular example, we are just toggling an LED on or off, and that is not it is not an operation that takes a long time. So we are going to do it right in the interrupt service routine. But when we get to path where we have to do long lasting operations, then I will show you how to use the flag approach. Now, you can't just go ahead and then say HAL GPIO toggle pin. The reason is that there are actually multiple ways of handling these interrupts, and this is the first one I'm showing you here. Remember in the theory lesson, I told you that when an interrupt happens, the EXTI sets a particular bit in the register that is known as pending registers. Okay, so basically, let's not get too deep into this stuff until we get started with the bare metal. But when an interrupt happens, one of these registers, I know which particular register, but I'm just saying one of these because I don't want you to bother yourself about it. One of these registers here will set some particular bit to indicate that an interrupt has happened on a particular EXTI line, right? And then that is what is going to cause the NVIC to trigger the processor to go and execute the interrupt service routine. Now, the problem is if you don't clear the fact that this interrupt has happened and it has been responded to, that bit is still set. And what it means is that it will keep, EXTI will keep indicating to NVIC that, hey, there is an interrupt here, and then the processor will come back to execute the ISR, and then it happens again and again and again, even though you have handled it. So it is your duty as the firmware developer to first of all clear the bit before you do what you have to do. Or if what you have to do could fail, then you can do what you have to do, and then when you finish, you check whether it worked or not, and then you can clear it. But clearing the bit that indicates that this interrupt has happened is your work. So this is how you do it. You do if there is a function __ HAL GPIO EXTI. So this is checking, okay? This is checking. We are getting, so EXTI get IT, and then we want to get to check, sorry, GPIO pin 0. Lord, I hate the IntelliSense in this IDE. It's not equal to reset. So what we are doing here is basically checking that if the bit that EXTI set to indicate that there has been an interrupt from this particular pin has been set. You see, we said if it is not reset, then we want to clear it first to signify that, okay, we have acknowledged this interrupt and we have actually handled it. Okay, so we want to clear it. So GPIO pin 0. Okay, so we clear it, and then now we do what we have to do. So what do we want to do? We just want to toggle the LED, right? So GPIO toggle, and then we want to toggle the LED on GPIO E, and the pin is GPIO pin 9, I believe. Okay, so I'll do a recap and then we will run this. So on line 21, we are telling the NVIC to, prepare itself to be checking for interrupt that happens on EXTI 0. And the reason is because the button that has been set up to raise an interrupt on the rising edge is connected to EXTI 0, as you saw from this diagram. I'm so sorry I'm repeating myself, but it is very important to get this. Otherwise, you will fail at what you intend to do. And once that has occurred, the next thing we want to do is to provide the interrupt service routine. The only reason I'm using the name EXTI0 IRQ and IRQ handler is because it is defined in the vector table. For now, you don't know what a vector table is. I will talk about vector tables in the next episode. So just take it from me that there is something somewhere called vector tables, and the names that I use there is what you have to use to define your interrupt service routines. So EXTI0 IRQ handler is the interrupt service request handler when there is an interrupt on EXTI0. Now, because EXTI set a particular bit to indicate to NVIC that an interrupt has happened, when we handle it, it's our job to clear it. So first of all, we check. And the reason for this check here is because from this diagram again, it is possible that the interrupt could come from either PA0, PB0, PC0, PD0, PE0, PF0, PG0, PH0. So we want to check the source of the interrupt to be sure that is the interrupt we are looking for before we clear it. So you check if the interrupt was raised by GPIO pin 0, then you clear it. Then you can go ahead and then do whatever it is you want to do. So now I'm going to click here to build this project. Waiting for it to build. Okay, build successful, and then now we can run the code here. So I've clicked for it to flash the code onto the microcontroller unit, my board, and let's wait for it. Okay, so it has finished downloading the code, so I'm going to switch, and then here let me position this somewhere that you can see it properly. So you see, when I press, okay, I think I know why. Let's go back to the desktop. There is a mistake in the code we need to fix. This thing here is toggling. This line 24 is toggling, so that's was the reason why it's blinking. So I'm going to take it off, and then we just let the processor have a breathing space of just 10 milliseconds. So I'm going to click this guy to rebuild the project. Okay, says done. I believe so. Then I can click to upload the latest code onto the board so we can see the effect of what we just did. Alrighty then. So now if I switch to the workbench, so you can see the microcontroller unit, you can see that it has stopped blinking, right? And when I press this, the LED turns on. When I press it again, it goes off. When I press, it turns on. When I press, it goes off. I really want a very good camera. Like, this is blurry, and sometimes I struggle to get the focus that I need. But I mean, you can see it working here. So let's go back to the code. So, ladies and gentlemen, this is how you use interrupt to detect external events that are happening on the GPIO pins, and then you get the processor to stop whatever it was doing, come attend to the interrupt that is responding or executing the interrupt service request, and then it goes back to continuing from where it left off. I know there are certain things I mentioned here, vector tables, interrupt service routines and stuff that could easily get over your head if you are not experienced in these things. So what I'm going to do in the next episode is to talk about the vector table and how the processor even begins to execute your code to get started with. Thank you very much for watching this, and I will see you in the next video.